Alright, in this video we're going to take a short look at the properties of liquids and liquid state as part of the unit on liquids and solids in advanced chemistry. Properties of liquids, and as we go over them, I want you to compare them to those of gases that we've already studied. Liquids and solids have very low compressibility. A liquid can be compressed, but only by a very, very small percentage of its volume. Similarly, liquids have very limited ability to expand. Now, gases, we know, can be highly compressed and are highly expandable. They fill their containers, in fact. Liquids do not possess anything like that in compressibility. Now, having said that, one important aspect of the compressibility / expansion of liquids is the expansion of the oceans that is occurring right now as a result of climate change. A lot of the heat that's going into the oceans is causing not only the temperatures of the oceans to rise, but it is causing the oceans to expand slightly. Now, given the volume of the oceans, very small expansion due to global warming will result in significant sea level rises along the shore. So although liquids have very low compressibility in the sense of ocean expansion due to climate change, it's actually a significant effect. Liquids, like gases, do not have any kind of definite shape. They take the shape of whatever container they're put in. Similarly, we can talk about the density of liquids. Compared to gases, the density of liquids is very high. Ranked, we would say solids generally have the highest densities, liquids are moderate, and gases have very low density. Just to compare, if you calculate the density of a gas at STP, you're going to find that the density is 1, 2, 3 grams per liter. But if you calculate the density of a liquid at STP, you're going to find its density to be in the hundreds or thousands of grams per liter. So liquids are much, much more dense. The particles of liquid, remember, are much closer together than in the gas state. The liquid particles are separated on average by less than 1 molecular diameter, whereas in the gas state at STP, there may be 10 molecular diameters between particles. So given that the particles are much closer together in the liquid state, the density is going to be much higher. The properties of liquids are going to be related to the intermolecular forces between particles. And so it's important to make a quick distinction between the forces that are experienced by particles in the liquid at the surface versus the particles in the liquid below the surface. If you are an interior molecule, if you're a molecule somewhere in the inside of the liquid below the surface, you experience intermolecular forces to your neighboring particles in 3 dimensions all around you. You'll be pulled upwards, downwards, left, right, front, back. You're attracted to all the particles around you in 3 dimensions. However, if you're a molecule or particle at the surface of the liquid, you don't experience any intermolecular forces from above. You're at the surface. There are no liquid particles above you. So therefore, particles at the surface experience the intermolecular forces to their neighbors only from below and to the sides. Now, one simple result of that is that because of the uneven forces experienced by particles at the surface surface particles will be pulled inwards, and that will create a spherical drop or a spherical bead of liquid. You've all seen water dripping out of a faucet or water beating up on a freshly waxed surface. They form those droplet shapes because of the intermolecular forces pulling the particles inwards but not upwards from the surface. We're going to talk broadly about 2 types of forces experienced by the liquid particles. Those are cohesive forces and adhesive forces. You may have discussed these in a biology class. Remember that the prefix co means together, and so what we're talking about with cohesive forces are the intermolecular forces between the between the liquid molecules themselves. So the one liquid particle attracted to a neighboring liquid particle, that's going to be a cohesive force. When you have strong intermolecular forces like dipole-dipole forces or hydrogen bonding, you're going to get strong cohesion between the liquid particles. One of the results of cohesive forces is called surface tension. If you've ever seen a spider or something, an insect, run across the surface of water, you've seen surface tension in action. Surface tension has a very specific definition. Make sure you know this. It's the resistance of a liquid to an increase in its surface area. The water spider, the water bug, running across the surface of the water, its footprint, if you like, if it were to go into the water, would force the water particles to spread apart so that the foot of the insect could enter the water. The water particles are strongly attracted to each other and don't want to be forced apart. They don't want to increase surface area as a result. So because of the weight of the bug being so small and the strength of the intermolecular forces being so big, the insect is able to run across the surface of the water. And of course, some larger animals can do that as well. There's a lizard called the Jesus lizard, which colloquially, which runs across the surface of water at very high speeds. As soon as it slows down, of course, it will sink in the water, but it's able to run for short distances along the surface of the water because of surface tension. If you've ever seen water after a rain on a screen in the window, you'll notice film of water in each of the little squares of the window screen. That film of water is also the result of surface tension, the particles of water held together by strong cohesive intermolecular forces. A related property that can also be explained by cohesion is viscosity. You probably remember doing some experiments on viscosity in middle school. You probably measure or compared the viscosity of different liquids, perhaps by pouring them down a slope, down an incline, and measuring how long it takes for the liquid to flow down the surface, or perhaps dropping something into the liquid and seeing how long it takes to sink through the liquid. So viscosity is the resistance of a liquid to flowing. When a liquid flows very easily, flows very quickly, we say it has a very low viscosity. If it flows very, very slowly, it's a very viscous liquid. It has a very high viscosity. The strength of the intermolecular forces, the cohesive forces, are directly related to this viscosity. When the strength of those forces is high, the liquid tends to be very viscous. And when the strength of the forces is low, the liquid is less viscous. Now there's another factor that is related to the viscosity besides the cohesive forces, and that would be the molecular complexity. Large, complex molecules, very long molecules, many atoms in them, will tend to just physically get entangled with each other. And as they get entangled, they'll have a higher viscosity. They won't want to flow past each other. But when molecules of a liquid are very small, they tend to not get entangled as much, and therefore they'll have a higher viscosity, a higher rate of flow. So make sure you know both the definitions of surface tension and viscosity. Now, viscosity decreases with increased temperature. Okay, you might have heard the phrase that something is slower than molasses in January. Molasses, of course, a very thick, syrupy liquid, and in January it's very cold, and so the viscosity of that molasses is even higher in the cold January temperature. Why is it that when you heat up the liquid, say some thick honey which you're trying to pour, if you heat it up, the liquid will flow faster? Can you think of a reason why that would be? I know if your reasoning goes something like, at a higher temperature, the particles have more kinetic energy, with more kinetic energy, they're able to overcome the cohesive forces that are holding them together to a greater extent. So when more particles have more kinetic energy, they'll flow past each other more quickly because they can overcome those cohesive forces. Adhesive forces are a little bit different. And when we use the term adhesive, you might think of something like tape, masking tape, or Scotch tape. Those are commonly called adhesives. To be an adhesive force, now we're talking not about forces between the liquid particles themselves, but between the liquid and something else, typically the container. So some masking tape is considered an adhesive because it sticks to another surface. So when you have the liquid attracted to another surface, that's going to be called an adhesive force. The surface of the container, the surface that the liquid is interacting with, is made up of particles, and if those particles are polar and the liquid is polar, then there's going to be some dipole-dipole forces between the liquid particles and the particles in the surface. So when you have strong interparticle forces like that, polar liquid forces and polar surface forces, then there's going to be strong adhesion between the liquid and the surface. When you put a liquid onto a surface, we assume that the surface will get wet. Okay? If you pour water on a surface, you'll tend to think of it as getting wet. But let's think about that a bit more carefully. If you pour some water onto, say, some paper towel or onto a piece of paper, certainly the paper towel, or perhaps your clothing, it will get wet. The water will soak into the surface and wet it. On the other hand, if you take a car and wax the surface of the car, coat it with some wax, then when it rains, the water doesn't soak into the car's surface, into the paint on the car. Instead, the water will form droplets, little beads on the surface, and they'll just roll off the car's surface without wetting it. That's sort of what happens when you wear a waterproof jacket, or when you treat some shoes, leather shoes for example, to make them waterproof. What you're doing is you're taking the surface, which normally would get wet because the surface has strong adhesive forces to the water, and you're coating that surface with a material, wax for example, which is not going to form strong adhesive forces to the liquid. Wax particles are made of carbon and hydrogen, so they're nonpolar. And because they're nonpolar, they don't interact strongly with polar water molecules. Oil is the same way. A duck, which goes in and out of water very, very often, the duck has oily feathers, which means the duck can land in water, and then when it comes out of the water, its feathers are almost instantaneously dry. You've heard the phrase, like water off a duck's back. The water just sort of beads up and rolls off of the duck without wetting its feathers. So whether a surface will get wet or not is a question of adhesive forces. Remember that polar liquid particles will be strongly attracted to polar surface particles. Similarly, nonpolar liquids will be attracted to nonpolar surfaces. Capillary action is another important phenomenon that you should be able to define and describe. It's the spontaneous rising of a liquid up a tube. So when you put a capillary tube in a liquid, you might remember doing that in the lab, the liquid rises up the glass tube. Similarly, water will rise up through soil in a similar phenomenon, capillary action. It's the result of strong adhesion, again, between the liquid and the surface that the water is attracted to. It's also a result of cohesion between the liquid particles themselves. So both of those forces are occurring in capillary action. If you imagine the water molecules, let's talk about water in a cylinder. So we've got here on the left a picture of perhaps a graduated cylinder or a test tube, and we talk about the meniscus in the cylinder. Now some students think the meniscus always has a certain shape, but no, the term meniscus just means the surface of the liquid in the tube. When you put water in a glass cylinder, the water forms a very characteristic concave meniscus. So the edge of the water seems to creep up the sides of the glass. On the other hand, if you put water into a plastic graduated cylinder, you may have noticed that the surface of the liquid is almost flat. The water doesn't really form a concave meniscus in a plastic cylinder. Contrast here, mercury. Mercury is a nonpolar liquid, and it's being put into a glass cylinder. And if you compare the meniscus in these two pictures, the one on the left with water has the typical concave meniscus, whereas the one on the right with mercury, you see a convex meniscus. Now, why is that? The answer is cohesion and adhesion. The glass surface, comes from sand, and sand is made up of silicon dioxide. So the surface of the glass is coated with silicon atoms with oxygen atoms budding off of them. The silicon-oxygen atoms in the picture below, silicon is shown in dark gray and the oxygens are shown in red. So you can see the little red spheres attached to silicon atoms, and the silicon-oxygen bonds are polar. They're polar covalent bonds. The difference of electronegativity between silicon and oxygen is large enough to be polar. You can see the water molecules with the red oxygen atoms, and in this picture, little blue, although they're usually shown as white, hydrogen atoms. The intermolecular forces with dotted lines between the water molecules, those would be dipole-dipole forces, and in fact, with water, they would also be hydrogen bonding. Because the hydrogen is bonded to oxygen within the molecule, you get hydrogen bonding. But that those water molecules, because they're strongly polar, are attracted with adhesive forces to the oxygen atoms in the glass. And so the water starts to climb the surface of the glass because of that adhesion. Cohesion comes in because water molecules will attach themselves to the water molecules that are climbing the glass. They don't want to see that water molecule leave because of the cohesive forces. So it's sort of like somebody's climbing a ladder and other people are hanging on to that person as they climb. Eventually, the adhesive forces, the forces that are allowing the person to climb the ladder, become balanced by the weight of the water particles that are held on by cohesive forces, and then the water stops climbing the surface. It would be, again, to take our ladder analogy, a strong person with strong adhesive forces can climb that ladder, but if people are hanging off of that person, they're going to eventually, the weight of the people hanging off will stop that person from climbing the ladder. And then at that point, you'll have the characteristic concave shape to the water within the cylinder. When you put a nonpolar liquid like mercury, mercury is made up of just atoms of mercury, and those atoms are not polar, so you get London dispersion forces. You get relatively weak intermolecular forces between mercury particles. Now, having said that, mercury is a pretty large atom, so the London dispersion forces between mercury atoms are going to be relatively strong compared to other London dispersion forces. However, because the mercury is polar and the glass is studded with silicon-oxygen polar bonds, there's no attractive forces between the mercury and the surface. So the cohesion is relatively strong because of the strong London dispersion forces within the mercury, but the adhesion is relatively weak because the nonpolar mercury atoms are not strongly attracted to the glass surface. As a result, you see no climbing up the wall, and instead, because just like the water forming a spherical droplet, we talked about that earlier, the mercury tends to form a spherical surface, convex surface, as opposed to the concave surface we saw earlier. Now, if we showed a third picture, this time with water again, but not in a glass cylinder, but in a plastic cylinder, you'd see that the meniscus there is almost flat. And the reason it's almost flat is because the plastic is made up of carbon-hydrogen surface. There's no strong attractive forces between the water and the plastic. So therefore the water is not adhesively attracted to the plastic surface. So we'll stop there. That's a quick overview of properties of liquids, adhesive and cohesive forces, and related topics like surface tension, viscosity, and capillary action, as well as rationalizing the shapes of the meniscus of various liquids in cylinders.